Right, I'm just going to say a few words now about a project I'm involved in called Climb, about cloud computing in general and what we call virtual machines. And this is just to lay the groundwork for what you're going to be doing later when you actually log on to a remote server that happens to be a virtual machine. And I'm going to weave in a little bit of history of the discipline of microbial genomics so that you can see why we do what we do, why we're using cloud computing, what the problems are that we're trying to address. So I'm going to tell you a bit more about all this stuff in subsequent weeks, but just to give you a brief overview of the history of bacterial genomics. You know, I'm old enough to remember the golden era that started in 1995 and went on to about 2007, where we got the first genome sequences from bacterial pathogens, and slowly over a period of years, basically all the significant pathogens of humans, animals and plants all were sequenced, and we got the insights into pathogen biology. Then we started getting more than one genome from the same species. So now you sort of think, what? Really? We got hundreds of thousands of species, of genomes from species now, probably millions. But this was a time of great progress where we were actually starting to see things. But this, around 2007, this got replaced by a sudden fast-forward move where we were faced with what we called benchtop sequencing. So up until then, it was a very onerous and expensive thing to sequence a genome. It required a team of people. Whereas once we got to the benchtop sequencing side of things, a student, PhD student, could do their own sequencing, create their own many multiples of genomes, dozens, hundreds, and everything just moved forward, and it changed the way we thought about things. And George Church, who is he's half mad and half brilliant. He's a guy who works at Harvard on synthetic biology. You may have heard of him for his efforts to try and de-extinct the mammoth, the woolly mammoth. But he's done also loads of cool things like changing the genetic code of E. coli and all sorts of things. And he pointed out the irony, which is that usually when things get cheaper, you end up spending less money on them. So if the amount of the if your car got cheap and you could buy a car for £100, well, you pay a car for £100. You wouldn't buy 50 cars or 100 cars because the price has gone down by 50-fold or 100-fold. But what happened with sequencing was that people did do that. They actually, sequencing so cheap, we'll just do more of it. And so as it got cheaper and cheaper and cheaper to sequence, we just got more and more sequences. And this is what people call the bingo slides, the conference bingo slide. Nick Lohman often goes on about this. If you ever go to a talk about this kind of topic, this is one of the slides that people put up, something like this, to point out that the price drop for sequencing massively outperformed Moore's law. So Moore's law was a rule about how computing decreases. I think, if I remember rightly, is it every 18 months? It used to be that you could get the twice as much computing power for your money, and that was a rule that applied to computers over decades. But with sequencing, it just got so cheap that we used to joke that the cost of sequencing a bacterial genome would be pennies by now, and I'm not sure what. You can ask him next week what David's latest price is. It probably is pennies now, isn't it? When it started, I mean, the first bacterial genomes were costing $500,000, hundreds of thousands, and now they're down to pennies. So this has been a remarkable transformation. But can you see where this is going? This creates a problem, which is often called the drinking from the fire hose problem. Because now there's huge amounts of data out there. And every bacteriologist on the planet is awash with data. And people say it's like trying to drink from a fire hose. You just can't cope with this stuff. Certainly you couldn't cope with it using the methods that you were using 10 years ago or 20 years ago. It required a change of approach, a change of mindset, if you like. And one of the solutions that's been put forward is this idea of cloud computing. So, to state the problem, this is a slide that I borrowed from Lisa, who is Andrea's significant other. The problem is that microbiologists around the world, in the UK in particular, can't really exploit these large genomics data sets because they don't have the relevant computational resources to hand. And what we decided to do about 9 years ago, was to try and address that issue. So one approach is to actually use cloud computing. And I'll explain a bit more what cloud computing is like in a moment, but this provides an efficient approach. So it may be that every bacteriologist in the land now has, within a few hundred yards of their lab, a benchtop sequencer, a MySeq, or even now a palm-top sequencer like Nanopore. But does that mean that they all go out and buy loads and loads of servers and try and configure them and so forth? The solution that we proposed, and particularly a guy called Tom Connor was very vocal about this in the early days, was that we should be using cloud computing. It provides a much more efficient way of dealing with this, so that you set up all this stuff in the cloud and you can pre-configure the computational environment that you're offering the users in a way that makes it easier, makes it easy to standardize things, enhances reproducibility. And the average microbiologist, and I would say I'm an average. I haven't learnt to become as good a bioinformatician as Andrea. I can muddle through. Basically, you want to save your research time to do the things that, answering research questions and actually doing research rather than troubleshooting pipelines and installing things and all that. And so cloud computing what was the idea that was being put forward at that time. So how does this work? So here's an old pale male-style individual standing by a server in a data center. There's a rack of servers there. So we've got one of those servers. That's a piece of hardware, computer hardware, and we want to make the most efficient use of that hardware. And what cloud computing does is that a user wants to have a server of their own, but what happens is the system spins up what we call a virtual machine, which is a self-contained module that behaves as if it is in itself a piece of metal, an actual computer, but in fact it's run through what we call emulation. And that is basically taking up a part of this hardware. It's not taking up the whole hardware. It's a very powerful server. It can do lots of things at the same time. But the average user could make use of part of this. But other users also want to use this kind of thing, and they can slot in their own virtual machines on top of that hardware and make use of it. So it means that you're sharing this kind of resource between as many individuals as possible and making the best use of this bare metal. So what we did was set up this project called CLIMB. It was funded by the Medical Research Council, which is what funds your DTP. It's called Cloud Infrastructure for Microbial Bioinformatics. And this ran for 7 years. There is a little movie I made at the end of those 7 years to celebrate our success. Depends how you're feeling. I mean, maybe we could play it later just to wake you up because it's the afternoon. But we basically had 900 users, 300 groups, 85 universities and other institutions across the country use this facility. We set up over 4,500 of these virtual machines. And we actually won some awards from this magazine, HPC Wire, to actually for the best use of high-performance computing. And basically what this did was we provided The users was with an interface which we call BRIN. It was hatched up. This was started off as a collaboration between people in the West Midlands and Wales. One day when they went to Wales, they said, well, what are we going to call this? Oh, let's call it BRIN, which is, because we'd call the thing climb, BRIN is actually Welsh for hill. So that was just like an in-joke, if you like. And this was an interface that allowed the users to be able to fire up these virtual machines, to create the virtual machines. The virtual machines would be launched and would start up within minutes, and they would come with the operating system, Linux, pre-installed on the thing. And one of the things that we were able to do was to give the users root access to those virtual machines, which meant that they could install whatever programs they liked, do whatever they wanted with the configuration. And what we used was this virtual computing environment. We used this software called OpenStack, which basically sits between the bare metal, the actual computers, and the virtual machines, and actually makes the virtual machines and makes use of the hardware. And this was a collaboration between Warwick, Birmingham, Swansea and Cardiff, and we had this infrastructure at all 4 sites. This root access thing is something that some users said to them was revolutionary, because in their own universities, their IT people said, oh, we can't give you root access to one of our things. You could do all sorts of things. You could create havoc. And they just didn't feel confident to do that, whereas we said, no, you can have root access. Now, of course, with root access, they could do also, they could mine Bitcoin, you know, they could they could run their own websites, you know, all sorts of things. But we made sure in the terms and conditions they didn't do that. And in fact, there were some things that they couldn't do. I forgot what's the name of that thing for file sharing. BitTorrent. Yeah, we closed BitTorrent to them so that they couldn't BitTorrent stuff. One guy tried to BitTorrent because, in fact, they did. The NCBI made the databases available via BitTorrent, and someone tried using it and then got slapped down. But generally, we gave people power that they didn't otherwise have. Now, I'm not going to go into the details. I am a microbiologist by training. I run a very poor emulation of a bioinformatician, and certainly in this situation, it wasn't just bioinformaticians, because we actually had to have people who were really IT specialists in how to configure the hardware and how to run this OpenStack cloud software. So even someone like Andrea would probably, if I said, could you set up an OpenStack configuration? It sort of wouldn't want to. It's like, no, that's a specialist thing. So setting up all this infrastructure. So as I mentioned, we got the users, got BRIN, they interact with OpenStack, and then OpenStack interacted with all these other bits and pieces. And here's the kind of hardware that we had for anyone who's a tool techie. This is all very old now because we bought this 8 years ago. It was one of those strange things where the government had some money left over, and they said, oh, we're going to give some, I can't remember now, what is it? It was about 30 million they were going to give out on medical genomics, and we bagged £8 million. And of that, 4.6 million was spent on compute, on the hardware, and we had to spend it because it was equipment within one financial year of getting the grant. So we had a mad spending spree that year. It was quite big. And we also spent 1.8 million on building. We reconfigured space for bioinformatics and so forth. So it was all mad. And there's a paper, which I can give you a link to, that we wrote a few years ago, which described everything. Basically, someone in their lab will be running a load of servers. They'll be able to go and launch various services within those servers and run things like Galaxy. We had a graphical user interface that we called the Genomics Virtual Laboratory server as well, which was people found very useful. And at the end of there's a link to the paper there. There's some videos if you want to look at them. The website for the project was climb.act.uk. And you probably don't recognise the quote there. It's a quote to a Heineken advert from yesteryear, where they used to advertise Heineken as probably the best lager in the world. We said this is probably the largest computer system dedicated to microbiology in the world. And this is where we left it. We had this running for several years. Then it came to a time to renew it. It was basically running out. And to cut a long story short, after some fruitless engagement, we actually managed to dock into the MRC system, get some useful advice, and I actually wrote a new proposal to fund a successor project, which is called Climb Big Data. And this was just a figure from the application showing our kind of unique selling points that we were going to engage in: community engagement, infrastructure, tools and integration, and that we were building on this very stable, resilient environment with a proven vibrant interdisciplinary team. One of the things that changed was that we brought in the MRC unit in the Gambia came in. They didn't get any funding out of it, but they came in as kind of virtual partners. The Quadram Institute, we did get some. The grant is now held here, and we actually got some funding for staff. But this place also already had lots of funding for compute as well. But we started to harmonise the ways in which we were working. So the Quadram Institute came in as a partner as well, and has been involved in our developments. So this is a slide I stole from Lisa, actually. I think she stole part of it from me, and then I stole it back again. We got to the stage where we put in the proposal in 2019. We got the thing submitted. A few months later, I was completely stressed out when having written this like 25-page document to get the grant, they said, yeah, okay, but we want a business plan as well. So I had to write a business plan over the 5 years, because they said, we don't want you coming back in 5 years and asking for more money. You've got to come self-sufficient. But by March of 2020, we got out the virtual champagne because we had been given the funding. And then in April, we started. And you probably remember the way things went. It started right in the middle of the pandemic. So that's why it was virtual champagne, because by the time we got the news, we couldn't even meet up and celebrate together. And so we started this project in the middle of the pandemic. And it's a 5-year initiative. The Blarney that we put in, a cutting-edge, scalable, dynamic bioinformatics platform to support academic research groups, government agencies and health services. So one of the things that was already apparent, even when we were running Climb, was that we had built an interface with public health agencies. So Public Health England, as it used to be, we'd worked with them. They actually used our resources. One time when they had a problem with their own resources, they used ours for a short while. Public Health Wales, there was a lot of interaction between Tom Connor and the University of Cardiff and Public Health Wales. And this actually helped energise the relationships that we currently have. So the UKHSA, which is the successor to Public Health England, is a partner in this DTP. And that flows from the good relationships we've had through this project and other collaborations as well. So this is the current team that we have. I'm the principal investigator, which basically means, to come back to that analogy, I'm the one that has to herd the cats and try and get all these academics to sort of kind of march in roughly the same direction. Lisa is a project manager. She's currently just returning from maternity leave, doing her Keep in Touch days. Mavis, who's she's actually the wife of my former PhD student, Eben. So that's how we knew her, and we invited her in to come as a project manager to help relieve Lisa during the maternity. And Michaela also come in, who's part of the larger bioinformatics infrastructure here. And then you can see all the others here. So Andrew Page here came in as a co-investigator with us. Chris Quince was at Warwick when we put the proposal in, but not long afterwards he got headhunted and pulled over here. I think he has, if I remember correctly, he's got a 5%, he's got a toehold in Warwick still, but he's mainly here now. In fact, this slide's out of date because Sam Shepherd has moved from Bath to Oxford. And then we've got, so those are the kind of academic leads, if you like. Then we've got these research software engineers, which are people who are more like your traditional bioinformatician, building tools and gateways and pathways. And then we've got all these other people who are involved in running the infrastructure and the cloud computing side of things. This I just, as I say, I stole a lot of this from Lisa. This was just her kind of screen of where she'd got to in the first year or so of doing things, the things that we'd set ourselves as targets. So one thing that hit us fairly quickly was that with the COVID pandemic, we interacted with what they call COG UK, which is Coronavirus Genomics Consortium UK, and they basically did the sequencing of the SARS-CoV-2 genomes from the UK, and that was a collaboration between lots of academic labs, public health labs, all sort of stapled together, and the data was all run through our Climb big data infrastructure. So they actually, all the hundreds of thousands of genomes were stored, analysed and made available to the rest of the scientific community through our Climb infrastructure. I hasten to add that I played almost no role in that. I wrote the proposal, got the funding for us, but it was down to Tom Connor and Nick Lohman to sort out the details of how that actually worked. But the fact that we had this, we had the resource, but we also had the interface with the public health people, put us in an excellent position. And I think I said this morning that Norfolk alone, if it were a country, would have been 5th in the world for output of coronavirus genomes early in the pandemic. And I think the UK probably was in the top 1 or 2 or 3, must have been in the early days. Certainly the UK got off to a very quick start with getting the genomes out because of these, we had this infrastructure there. These are the things that Lisa's been doing, looking after our finance. You don't really worry about that. We've updated our users, we've expanded our infrastructure, we've sorted out service updates and so forth, and we've done a lot of training. So again, this is from one of her slides. One of the things we've been doing is moving towards self-sustainability. And you can argue about this one. You can argue, is it better for the research councils to just fund this centrally and say this is a core resource for the whole of the UK? It's most efficient to just run this centrally. They decided not to do that. They've decided that we have to now start charging the users. And so we're in a process of moving towards that model, and whether it's going to work or not, we don't know. We're moving towards a new usage model. So one of the problems we had with the old style was that we would give people, you could log on and say, I want a virtual machine. I'm doing my PhD, I want my own virtual machine, I'm going to do some work on it. And then you finish your PhD, you don't tell anyone, you just leave the virtual machine sitting there, and that takes up resource in the system. The virtual machine's not doing it, it's not turning over, no computation's been done, but it's blocking out resource. And even at the most basic level, that virtual machine has what we call an IP address, has an address on the internet. And those addresses are a finite resource as well. And so we kind of realised that this approach, where we didn't quite know whether the virtual machines were being used for anything, whether they've been used 24/7 or just left for months or years without anyone doing anything. Because one of the things we said was we're not going to put any kind of daemon inside your machine to check whether you're using it. We sort of thought, no, we leave this as a private thing for the user. And what they do, we don't want to have worries about their data, that we have access to their data. That brings responsibilities for us. And so that was an issue. We also, with the issue about people just having accounts, setting up virtual machines. A lot of it was just inertia. So we said, no, look, you're going to have to continue to tell us. So you would have to say, I've got this virtual machine, I am still using it, please don't shut it down. And you'd have to keep reminding us every 3 months so that we kept things going. One of the things that you can do with virtual machines, which is interesting, is that if you don't want to be using it actively, you can do what we call shelving it. So effectively it's just a file, and that file is holding the state of that virtual machine, whatever you were doing at that time, whatever's running, whatever files are on it. It's kind of held as an object, if you like, as a piece of code. And people have spoken about this, that maybe you could publish the virtual machine. So if you did a project for your PhD and you wanted someone else to say, well, you analysed 20,000 coronavirus genomes and you had your own way of doing it and you thought, I've got the best way in the world, you can share things like pipelines and tell people, here's the code, blah, blah, blah. But then there's all the dependencies and there's you could share the actual machine. And they could actually then, the idea was that you could take that virtual machine and use it. So that was another interesting idea. In fact, with the virtual machines, it turns out they're not really that mobile, it's not that portable. But you will be learning from Andrea later in the week. There is a development called containers, which are like cut down virtual machines, which is now a big thing, where you run things in containers, and that takes away all the hassle of dependencies and shit like that. And we spent some money also on improving our actual physical infrastructure with another cool development in bioinformatics at the moment is that people are using what they call graphical processing units, which are chips that have been designed for gamers to run their games on, but because of the economies of scale, and Nabil mentioned this as well, because gaming is such a big thing, it drives the economies of scale and efficiencies, and so you can buy these graphical processing units very cheaply, and they can do great things, but they're a slightly odd thing if you're trying to do bioinformatics, and people are having to try and get their head around how you make best use of them. Have I presented that the right way?
Absolutely.
Yeah, exactly.
I was thinking that recently gamers have been outbid by Bitcoin miners. So they are more their graphics card for that.
Yeah. So, Bitcoin was it supposed to produce more carbon emissions than the whole of France or something? Yeah. Strange world we live in. We're not just this bunch of people doing geeky things. We're actually engaged in community engagement. So we've had workshops, hackathons, symposia. We've been strengthening the capacity generally, and trying to encourage people to do things. So, for example, in hackathons, one of the things that you can do is you get a load of bioinformaticians together. You get Andrea, Nabil, and a few other people in a room together, and they say there's 5 or 10 different ways to assemble a bacterial genome, these pipelines and programs out there. Which is the best? Let's compare them all. Let's give them all the same data set and see how they perform. And they'll choose what their performance stats are, which one completes first, which one uses up least memory, which one gives the best results in terms of contiguity of the assembly, which one gives the most accurate results in terms, and and so we've been running these kind of things. Andrew Page in particular is a great fan of hackathons and loves all that sort of stuff. So this is just I borrowed this slide. It's slightly out of date now as well from Lisa, but it just shows you the sorts of things that we've been doing. And during the pandemic, there was this a lot of interest in this project called Arctic, where they were making workflows available for emerging infectious diseases, and obviously coronavirus, COVID was an emerging infectious disease that came out, and sharing the pipelines for analysing sequence data. And so, one of the things that I've said, and you can put me down as a soppy idealist, is that within this field of microbial bioinformatics and bioinformatics generally, there's a huge amount of goodwill, of people working together for the common good, giving up their time, not having their time, no timesheet and amount of money spent. They just do their job, share their resources. And it's a strange mindset. Some people just can't get their head around it. What on earth? You wrote a program and then just give it away for free? Why aren't you licensing it and making money and all that? And that is a direction we'd sometimes get pulled by the government. You're just a branch of the UK economy. You should be making money. But that's not the zeitgeist, if you like, among bioinformaticians. It's all to do with sharing. So we were part of that, sharing knowledge. And this, you'll be learning more about this later on as we go along. But some of these things here, like managing containers, these are cut down virtual machines, if you like. Running Jupyter Hub as a kind of way, and Galaxies are ways of interacting that allow you a bit closer to a graphical user interface and not everything done on the command line. And the thing is that if you could come up with a standard operating procedure for doing a thing, then it's perfectly fine to try and commoditize it, and turn it into something that you can access through this interface Galaxy, where I have 1,000 genomes, just go and quality control them, assemble them, blah, blah, blah. I just press the buttons and off it goes. That is a way of working, and that's what you provide, those kind of workflows, don't you? For people, postdocs who I don't care about the details, I just want to assemble these genomes, they can go to these kind of interfaces and do it. One of the things that I mentioned already was that Quadrum came into the Cloud Big Data project, but they have their own cloud infrastructure. So they had their own hardware that was bought through a separate funding stream, and it was agreed that they would set up their own cloud computing infrastructure using OpenStack, the same software that we're using, but they would just be slightly orthogonal to the rest of the Cloud Big Data project. So they're not, at the moment, the infrastructure here is not providing a resource for anyone else outside of Quadrum. The other sites, the other hosting sites, provide a virtual machine to anyone who has academic credentials in the UK and within remit. So if you're at the University of Aberdeen and you're doing microbial genomics, you can access those resources. What we've said here is that the plan, and it's one of those things I have to keep reminding Andrew about, I suppose, is that you did say that when you got to a stable situation, any excess capacity that you had that wasn't being used by people in Quadrum might be used by people outside. And we've not got to the stage where we've given people virtual machines here, but that has been used for workshops. I can't remember how many workshops they've run on the QRV Cloud, but it has happened, doesn't it? External. Oh, what's happened here? Someone's hijacked our connection. That's not on, is it? Who's that? Someone's done it over Wi-Fi.
Well, it might be an interesting thing.
Oh, well, if they're... Go in the other room and tell them off. Anyway, that was my last slide. It was basically to say that there is a core bioinformatics team here, and this is not good. So if they GMH research, gut microbes in health. He's gone to